X-rays. 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 Topics covered in this video are: Introduction to X-rays, Origin of X-rays, and Mosley Laws, Production of X-rays, Properties of X-rays, X-ray spectrum, Applications of X-rays. X-rays. An introduction. X-rays are widely known today in the field of medical science, security, industries and scientific research. On the 8th of November, 1895, German scientist Wilhelm Roentgen produced and detected radiations known as X-rays or Röntgen rays. For this achievement, he was awarded the first Nobel Prize in physics in 1901. In honor of his accomplishments, in 2004, the International Union of Pure and Applied Chemistry named element 111, Röntgenium, Rg, a radioactive element with multiple unstable isotopes, after him. X-ray is an electromagnetic EM wave. Noted on electromagnetic wave spectrum. X-rays are electromagnetic waves with high frequency and high energy and short wavelength. After its detection, it is found that X-rays travel in straight lines from the source. X-rays cannot be deflected by electric and magnetic fields, which shows that they are not charged particles. Reflections, diffractions, and interference of X-rays are in the same ways as that of light and others electromagnetic waves. X-rays are a form of electromagnetic radiation with high energy and short wavelengths, allowing them to penetrate various materials and interact with matter in ways that produce images or provide insights into material structure. The product of wavelength lambda and frequency f or nu is the wave's propagation speed. That is the speed of light c. Therefore c equals nu times lambda. The X-rays wavelength lambda are short and their frequency nu are high, as the energy of the wave is given by equals h nu. So the energy X-rays is very high. X-ray photon energies typically range from 100 electron volt to 100 kilo electron volt or 100,000 electron volt. This corresponds to wavelengths from 10 nanometers to 0.01 nanometers. X-rays with energies around 100 electron volt are at the lower end of the X-ray spectrum. X-rays with energies around 100 kilo-electron-volt are at the higher end of the spectrum. The photon of energies over typically 100 kilo-electron-volt are considered gamma rays. Simple conversion of energy and wavelength. 1 kilo-electron-volt of energy of photon has wavelength 1.24 nanometers. Or 100 kilo-electron-volt of energy equals 0.124 nanometers wavelength. For X-rays, we talk about its energy and wavelengths, as their frequencies are very high. For normal conversation, X-rays wavelengths in the range of 0.01 to 10 nanometers corresponding to frequencies in the range 30 petahertz, 10 to the power of 15 Hz, for lambda equals 10 nm, to 30 exahertz, 10 to the power of 18 Hz, for lambda equals 0.01 nm. X-rays up to about 10 kilo-electron-volt, 10 to 0.10 nanometers wavelength, are classified as soft X-rays, and more than 10 kilo-electron-volt to 120 kilo-electron-volt as hard X-rays, due to their deeper penetrating abilities. X-rays. A quick history review. The history of X-rays begins with their discovery in 1895 by Wilhelm Conrad Röntgen, a German physicist. On November 8, 1895, while experimenting with cathode ray tubes at the University of Würzburg, Röntgen noticed that a fluorescent screen glowed even when shielded from visible light. He identified this as a new type of radiation, capable of penetrating solid objects, which he called X-rays, due to their unknown nature. First X-ray image. In December 1895, Röntgen produced the first X-ray image, a radiograph of his wife Anna Bertha's hand, revealing bones and a ring. This demonstrated X-rays' potential to visualize internal structures non-invasively. Röntgen published his findings in On a New Kind of Rays in December 1895. He did not file patent and charged anything and shared his discovery freely. He received the first Nobel Prize in physics. Had he not received Nobel Prize in physics, he would have got it for medicine. In early adoption of X-rays from 1896-1900s. Medical applications. Within months, X-rays were used for medical diagnostics. In 1896, physicians like John McIntyre in Scotland and Walter Bradford Cannon in the US began using X-rays to image fractures, foreign objects, and diseases like tuberculosis. There was a huge public fascination. X-rays captured public imagination, appearing in newspapers and even leading to novelty uses, like X-ray studios for portraits. However, early misuse, that is capturing in shoe-fitting fluoroscopes, raised safety concerns. Technological improvements. Early X-ray tubes, or Crookes tubes, were used up to 1920, and later used were those refined by William Coolidge in 1913, which has improved reliability and image quality by using heated filaments to produce X-rays more efficiently. Safety. Awareness. The harmful effects of radiation, such as burns and cancer, became evident at early stages of misuse of X-rays. Lead shielding and dosage limits were introduced to protect patients and operators. During the period of from 1930 to 1950, diagnostic expansion took place. X-rays became standard in hospitals for diagnosing bone fractures, dental issues, and chest conditions. Fluoroscopy allowed real-time imaging, aiding procedures like barium studies. Fluoroscopy is a medical imaging technique that uses X-rays to provide real-time, moving images of the body's internal structures. It is essentially an X-ray video, instead of snapshot taken by X-ray, allowing doctors to observe organs, tissues, and other structures as they function. Computed tomography, CT, developed in 1970. A major leap came with the development of CT scans, pioneered by Godfrey Hounsfield and Alan Cormack, who got the Nobel Prize in 1979. CT computed tomography used X-rays with computer processing to create detailed cross-sectional images, revolutionizing diagnostics. Mammography and angiography. Specialized X-ray techniques emerged, like mammography for breast cancer screening, and angiography for visualizing blood vessels. In modern developments, from 1980s to present, digital X-rays in 1990s is the major highlight. Film-based radiography is transitioned to digital systems, improving images and its storage, sharing, and analysis while reducing radiation doses on patient. Advanced applications. X-rays are now used in interventional radiology, guiding minimally invasive surgeries, and in research, like crystallography, XRD X-ray diffractometers. Safety and regulation. Modern standards, like those from the International Commission on Radiological Protection, ICRP, minimize radiation exposure with low-dose protocols and alternatives like MRI, reducing X-ray use in some cases. Today, X-rays are used in material science, security, like airport scanners, and astronomy, that is studying black holes by X-rays telescopes. Wilhelm Roentgen's discovery remains a cornerstone of modern science, with ongoing innovations in imaging technology. Production of X-rays. Sir Wilhelm Roentgen discovered X-rays accidentally while working on high-energy electron beam, also known as cathode ray. Based on his experiment, he designed an equipment to produce fast-moving electron and directed these electrons to some metal target, which produced X-rays. Even today, X-rays are produced based on this experiment, and they are called X-rays tube. There are two basic types of X-ray tubes, namely A. The gas-filled or Crookes tube's X-ray tube. B. The Coolidge tube or hot filament tube. Crookes tubes. Crookes tubes were the earliest form of X-ray tubes. and are also known as cold cathode tubes. In this X-ray tube, a partially evacuated glass bulb, a concave cathode of aluminium, is placed to produce and focus a beam of electron cathode rays on the tungsten target. Crookes tubes generated the required electrons to create X-rays by ionization of the residual air or gas in the tube. The flat metal target, which acts as anode, and also known as anticathode. The target is inclined at an angle of 45 degrees to incoming beam of electrons. The inclined target to incoming beam of electrons is to gives direction to produced X-rays perpendicular to electron beam. Remember, first, we need a cathode and an anode to create ion plasma, a colored discharge, and one anticathode or target at a high voltage to attract electron at high speed and energy. The voltage is provided to the tube between cathode and target anode by an induction coil, producing ranging from 1000 volts to 100 kilovolts. The cathode rays or electron beam fall on the target and hence X-rays are produced. In later X-ray tubes, the target is combined with anode. What a Crookes tube. Electrons travel in straight lines from the cathode as shown by the shadow cast by the metal cross on the fluorescence of the right side glass wall of the tube. The anode to produce ion plasma is the electrode at the bottom. When the voltage applied to the tube is not very high, the X-rays produced are soft. The higher voltage between cathode and target anode accelerate the electron faster, hence giving them more energy and produces high energy or hard X-rays. The functioning of the tube depends on the pressure of the gas inside the tube. The number of target of different metals were tried and it was found that a target will be better and produces X-rays if it has 1. High atomic number, 2. High melting point, 3. High conductivity towards heat and electricity, 4. Low vapor pressure at high temperature. The target of different metals were tried and following targets are found better: tantalum, platinum, tungsten, molybdenum, rhodium. See on table: tantalum, platinum, tungsten, molybdenum, rhodium. The life and performance of the Crookes tubes were unreliable. As time passed, the residual air would be absorbed by the walls of the tube, reducing the pressure. This increases the voltage across the tube, generating harder X-rays, until eventually the tube stopped working. The defects of the Crookes tubes are shortlisted as 1. The intensity of the X-rays and the quality of X-rays cannot be controlled. 2. The softening device is not perfect, and the applied voltage required is very high. We continue with the production of X-rays. Coolidge X-rays tube. This X-ray tube was designed by Coolidge in 1912. The main feature was it had a hot cathode to produce a beam of electrons. The Coolidge tube, also called hot cathode tube, is the most widely used. In this tube, the electrons are produced by thermionic emission from tungsten filament, heated by an electric current. The filament is also act as the cathode of the tube. Other difference was it operate in total vacuum of the order of 10 to the power of -6 torr. Hence, we see no ionization of gas plasma for electrons. By adjusting cathode current, both the intensity and the quality of the X-rays can be controlled. Here is a diagram of X-ray tube. A glass bulb, a cooling chamber around the anode to cool it. Anode is attached with target. A filament of other side, connected to 6-volt DC. The anode and cathode are connected to very high voltage. Filament is heated. Electron beam is out. Hit the target. Produces X-rays and directed to the window of the tube. Note: the electron beam is focused on the target. Such an arrangement is known as electron gun. The target is cooled by fan or by water coolant. The high voltage is taken from a large step-up transformer of AC supply. The X-ray tube works as its own rectifier, and the current will pass only in half cycle. The tube is enclosed in a lead box of 5 mm thick wall, and a small window is provided to pass the X-rays. The highest voltage X-ray tube uses about 1,000,000 volts and produces X-rays of 0.1 nanometers wavelength. The anode is precisely angled at 20 degrees off, perpendicular to the electron current, so as to allow escape the X-ray photons, which are emitted essentially perpendicular to the direction of the electron current. The anode is made of tungsten or molybdenum. The power of a Coolidge tube usually ranges from 0.1 to 18 kW. In further developments of X-rays tube, after the successful Coolidge X-rays tube, two designs were suggested and tried. End window tubes and side window tubes emerged in the market. End window tubes have transmission target, which is a thin metallic target, to allow X-rays to pass through. X-rays, which are emitted in the same direction as the electrons are moving. A typical end window X-ray tube. The special features of side window tubes are: an electrostatic lens focuses the beam onto a very small spot on the anode. The anode is specially designed to dissipate the heat and wear resulting from this intense focused barrage of electrons. In further developments of X-rays tube, during 1940s and 1950s, rotating anode tube were employed to minimize heating of anode in the tube. A spinning anode disc dissipated heat more effectively, enabling higher intensity X-rays. This was patented by General Electric in the 1930s, became widely used in medical diagnostics and industrial imaging. Further development in X-rays tube focuses now to miniaturization and specialization, improvements in electronics and cooling systems allowed for smaller, more efficient tubes, specialized tubes designed for applications like dental imaging, fluoroscopy, and radiotherapy, with refined focusing and filtration to improve image quality and reduce patient radiation exposure. Until the late 1980s, X-ray generators were merely high-voltage AC to DC variable power supplies. In the late 1980s, a different method of control, called high-speed switching, switch mode power supply, emerged and allowed for more accurate control of the X-ray unit, higher quality results and reduced X-ray exposures. Some of the recent advancements include dual-energy X-ray tubes for enhanced material differentiation in medical and security imaging, and carbon nanotube-based tubes for compact, efficient X-ray sources. Developed were high-power tubes with advanced cooling to support cutting-edge applications like 4D, CT scan, and image-guided radiotherapy. Properties of X-rays. X-rays are not deflected by electric and magnetic field, as they have no charge. They are highly penetrating and can pass through many solids such as wood, clothes, flesh, etc. They cause fluorescence in many substances, like barium, Plato cyanide, cadmium, tungsten, zinc sulfide, etc. X-rays affect a photographic plate. They ionize a gas and also knock out electrons from certain metals on which they fall. This effect is known as photoelectric effect. They travel in straight line with velocity of light. X-rays show reflection, refraction, interference, diffraction, and polarization in the same way as light. Today, highly coherent X-ray laser are also made and being used in very special application and research field. Scattered X-rays. They are practically of same nature and wavelength as the primary X-rays. Their properties do not depend upon the nature of the scattering substance. Origin of X-rays. X-rays were discovered and used much before the accepted modern model of atom was established. With this atomic model, many observations of spectrum were explained. To understand the X-rays, the spectrum of different X-rays tube were studied. X-ray spectrum. It would be nice and simple if all of the X-rays coming out of an X-ray tube had the same energy, a so-called monoenergetic X-ray beam. But in reality, X-rays coming out have a variety of energies. It is useful to examine the different energies in an X-ray beam. X-ray spectrum. This is termed the X-ray spectrum and is essentially a plot of the number of X-rays for each given energy. It is like the spectrum of sunlight, which has all the colors, and based on its study, we are today making very specific colored source, such as LED and lasers. Spectrum of white light by Newton, demonstrated using a glass prism. Coming back to X-ray spectrum, it is important to know the number of X-ray photons and the energy of the X-ray photons that come out of X-ray tube to determine how much radiation dose is used in a given exposure. For each kilovolt of power setting, the spectrum of X-ray photons were studied. It is noticed that the spectrum of X-rays is different if the target element or metal is different. The spectrum of X-rays contains not only sharp lines of short wavelength, but also a continuous spectrum in that range of the wavelength. Here is a typical X-ray spectrum. On y-axis intensity of X-rays are shown and on x-axis energy or wavelength is taken. First notice continuous X-rays. On left side of x-axis is high energy and on right side it is longer wavelength and lower energy. Now note, lines are due to characteristic X-rays. K beta K alpha lines, L beta L alpha lines, M beta M alpha lines. In the X-ray spectrum, the sharp lines in the spectrum were related to the material of the target and its atomic number. The sharp lines suggest that the X-rays are originated from the jumping of an electron from one orbit to another, as it is generally a case of many emission spectrum. While the continuous spectrum is explained through phenomenon of Bremsstrahlung. For each kilovolt of power setting, the spectrum of X-ray photons generated by Bremsstrahlung interactions is more or less a linear function. For further understanding, we look at the spectrum in two parts. Continuous X-ray spectrum. When high-speed electrons bombard a target material, they can be decelerated and deflected by the atoms in the target material. This deceleration process, like applying brake, releases energy, results in the emission of X-rays across a range of wavelengths, forming a continuous spectrum. Here we take continuous X-ray spectrum. To explain continuous spectrum of X-rays, it is referred to as Bremsstrahlung, which means breaking radiation in general. In this process, the high-energy electron passes through the atom. It is attracted by the positive charge of the nucleus. Its momentum breaks and is get deflected. In this process, it loses its kinetic energy in the form of radiation. Noted here. Movement of fast-moving electron. An X-rays that coming out by deflection and change in velocity of electron. The kinetic energy is half mv square. The kinetic energy is half mv square. Changes to the kinetic energy is half mu square. Electron interact at a distance, produce low energy of longer wavelength, soft X-rays, which is the difference of initial kinetic energy and final kinetic energy of electron. The kinetic energy half mv square minus half mu square equals h nu. Noted here. Movement of fast-moving electron close to nucleus. An X-rays that coming out by deflection and change in velocity of electron and its the kinetic energy. Electron interact at a close distance to nucleus, loses more energy and produces moderate energy X-rays. He kinetic energy half mv square minus half mu square equals h nu. Origin of X-rays. X-rays. Bremsstrahlung spectrum. Also in this process, if the high-energy electron attracted by the positive charge of the nucleus hits the nucleus, it may lose all its kinetic energy during the impact. It will produce maximum energy X-ray. Half mv square equals h nu. Simple conversion of energy and wavelength. 1 kilo electron volt. Energy of photon has wavelength 1.24 nanometers. Watch it in animation. X-ray spectrum. It has a sharply defined short wavelength limit, given by lambda minimum equals 1240 divided by number of volt in angstrom. The cutoff wavelength, lambda minimum, is independent of the nature of the target material, but is inversely proportional to the potential difference between the cathode and anode of an X-ray tube. Note here and understand. As shown in the typical graph, the value of lambda minimum decreases as the potential difference is increased. X-ray spectrum. The intensity of the continuous spectrum is found very nearly proportional to the square of the applied voltage for a given target, and the atomic number of the target material when a constant potential difference is applied. There is a shift of maximum intensity position towards the short wavelength side as voltage is increased. Now we talk about characteristic X-ray spectrum. When a high-energy electron interacts with an atom, it can knock out an inner shell electron. This creates a vacancy or hole in the inner shell, which is then filled by an electron from a higher energy level. This electron transition releases energy in the form of an X-ray photon with a wavelength characteristic of the target material. These characteristic X-rays appear as sharp peaks superimposed on the continuous spectrum. Note the characteristic X-ray spectrum. Lines are due to characteristic X-rays from high energy side to lower energy side. K beta, K alpha, L beta, L alpha, M beta, M alpha. Characteristic X-ray spectrum. Note it again. When a high-speed electron from the cathode strike the target's atom, then this high-energy electron eject one electron of the atom from one of its lower orbits, K, L or M. The electrons create a vacancy or hole in lower shell or orbit. To fill the space created by leaving electron from lower orbit, K, the electron comes from higher orbit, L or M, to lower orbit. This electron from higher orbit radiates extra energy in the form of X-rays photons. We get the K alpha line if electron comes from L orbit, and the K beta line if electron comes from L orbit. Try to understand here with this animated diagrams. Characteristic X-ray line, K alpha. Watch the action of the fast-moving electron. An ejected electron, along with outgoing electron. Watch how an electron from L orbit moves to fill vacancy in K shell and releases X-rays of K alpha line. K alpha, h nu equals energy of L orbit minus energy of K orbits. Now note same action 4. Characteristic X-ray line, K beta line. Watch the action of the fast-moving electron. An ejected electron. Along with outgoing electron. Watch how an electron from M orbit moves to fill vacancy in K shell and releases X-rays of K beta line. K alpha, h nu equals energy of M orbit minus energy of K orbits. Characteristic X-ray spectrum. This kind of X-rays results from a sufficiently strong interaction that ionizes the target atom by a total removal of the inner shell electron. The resulting hole in the inner shell is filled with an outer shell electron. Characteristic X-ray spectrum. The transition of an orbital electron from an outer shell to an inner shell is accompanied by the emission of an X-ray photon with an energy equal to the difference in the binding energies of the orbital electrons involved. Therefore, the characteristic radiation produces a line spectrum or discrete spectrum. Obviously, this kind of radiation is material dependent. Both the production of characteristic X-rays as well as thermal energy involve interactions between the accelerated electrons and the electrons of the target material. We take as example of target material tungsten. Chemical symbol W. Tungsten, of atomic number 74, consists of a nucleus containing 74 protons and 110 neutrons surrounded by 74 electrons. K shell, L shell, M shell, N shells refer to the first 4 electron shells of an atom, designated by the principal quantum numbers n equals 1, 2, 3, and 4 respectively. They represent the different energy levels that electrons can occupy around the nucleus of an atom. Watch it on energy level diagram. With energy level of K, L, M, N, and O. Note here how the line K alpha, K beta, and K gamma are designated. Now, note here how the line L alpha, L beta, and L gamma are designated. The line M alpha and M beta are designated. Discrete spectral lines K series, L series and M series etc. K series, K alpha, K beta, K gamma, consists of the lines depending the electrons which occupy the vacancy in K orbit come from L, M or N. K series being most energetic, constitute the hard X-rays, whereas L series and M series form the soft X-rays. Line spectrum is the characteristics of the target material used. The number of lines present in the spectrum depends both on the nature of the target material and the excitation voltage. Some data are given in following table. K-shell characteristic X-ray energies in kilo-electron-volt of common X-ray tube target materials: tungsten, molybdenum, rhodium. Electron binding energies in kilo-electron-volt of common X-ray tube target materials: tungsten, molybdenum, rhodium. Please note, electron binding energy, also known as ionization energy, is the minimum energy required to remove an electron from its atomic orbital. Factors affecting the X-ray spectrum. 1. Target material. The target material determines the wavelengths of the characteristic X-rays. 2. Voltage. Increasing the voltage applied to the X-ray tube increases the kinetic energy of the electrons, resulting in higher energy X-rays and a wider range of wavelengths in the continuous spectrum. 3. Current. Increasing the current increases the number of electrons, and thus the intensity of the X-rays produced. With the analysis of K-line spectrums, it is noticed that there is a regular shift towards shorter wavelength with the increased atomic number of the target. The exact relationship comparing two target material is given as nu2 divided by nu1 equals Z2 minus 1 squared divided by Z1 minus 1 squared, where nu1 is the frequency of K alpha line for a target material having atomic number Z1, and nu2 and Z2 are similar quantities of different target material. Mosley's Law. Mosley's Law, by the English physicist Henry Mosley in 1913, is an empirical law concerning the characteristic X-rays that are emitted by atoms. Mosley derived his formula empirically by fitting the square root of the X-ray frequency plotted against the atomic number of the target materials. Mosley was able to show that the frequencies nu of certain characteristic X-rays emitted from chemical elements are proportional to the square of a number which was close to the element's atomic number Z. Nu equals A times Z minus B squared. According to Mosley's law, 1. It is the atomic number of an element and not the atomic weight which accounts for the physical and chemical properties of an element. 2. This law provides the guidance that elements must be arranged in periodic table according to their atomic number, not according to their atomic weights. Three. By considering the X-ray spectra of rare earth elements, this law has been helpful in determining their atomic number and also fixing their position in the periodic table at appropriate positions. 4. This law also led to the discovery of some new elements like hafnium, atomic number 72, promethium, atomic number 61, etc. Mosley derived his formula empirically by fitting the square root of the X-ray frequency plotted against the atomic number, the square root of the frequency, square root nu, of an element's characteristic X-ray emission is linearly related to its atomic number, Z, expressed as square root nu equals A times Z minus B, where A and B are constants. Square root nu equals A times Z minus B, where A and B are constants and depend on the type of X-ray line, like K, L, etc. For K series, the value of A is square root 3RC divided by 4, and that of B is 1. Here R is Rydberg's constant, and C is speed of light, as in Bohr's model. For L series, value of A is square root 5RC divided by 36, and B is 7.4. The relation and values of A and B are experimentally determined by Henry Mosley. To understand, we take an example. If lambda Cu is the wavelength of K alpha X-ray line of copper, atomic number 29, and lambda mo is the wavelength of the K alpha X-ray line of molybdenum, atomic number 42, we find the ratio wavelength of X-rays by Mosley's formula. The relationship is nu 2 divided by nu 1 equals lambda 1 divided by lambda 2 equals Z2 minus 1 squared divided by Z1 minus 1 squared. Substitute the value of Z to get lambda Cu divided by lambda mo equals Z mo minus 1 squared divided by Z Cu minus 1 squared equals 42 minus 1 squared divided by 29 minus 1 squared equals 2.14. Until Mosley's work, atomic number was merely an element's place in the periodic table and was not known to be associated with any measurable physical quantity. In brief, the law states that the square root of the frequency of the emitted X-ray is approximately proportional to the atomic number. Significance of Mosley's law. Organizing the periodic table. Mosley's law provided a more accurate way to arrange the periodic table, correcting discrepancies that arose when using atomic weights. Significance of Mosley's law. Discovering new elements by identifying gaps in the X-ray spectra. Mosley's law helped predict the existence and atomic numbers of undiscovered elements. Understanding atomic structure. The law solidified the concept of atomic number as the fundamental property of an element and its relationship to the nucleus's positive charge. The law is closely linked to Bohr's model of the atom, where electrons transition between energy levels, emitting X-rays with frequencies related to the energy difference. Mosley's work provided experimental evidence supporting Bohr's model and the concept of quantized energy levels. Applications of X-rays. Applications of X-rays in medicine. X-rays have a wide range of applications across various fields due to their penetrating and imaging capabilities. X-rays can pass through the flesh and not through the bones of human body. Therefore, X-rays are of extensive use in surgery to detect fractures, foreign bodies, diseased organ, etc. A typical X-ray room of a hospital. X-rays have diverse applications in the medical field, primarily for imaging and treatment. In diagnostics, X-rays help visualize bones, detect fractures, identify tumors, and assess lung and heart conditions. Fracture detection. X-rays is a primary tool for identifying broken bones and assessing the alignment of fractures. Medical diagnostics. Imaging bones to detect fractures, dislocations, or abnormalities. Note here in the picture a broken arm's bone, lung and heart conditions. X-rays can reveal abnormalities in the lungs, such as pneumonia or tumors, and can also be used to assess heart size and potential issues. A typical chest PA X-rays is used to examine lungs for infections, pneumonia, or tumors. Note here. How are they diagnosed? Joints, shoulder, bones, ribs, soft tissue, heart. Tumor identification. They can help detect various types of tumors, including bone tumors and some kind of lung tumors. X-rays kill the diseased tissues of the body. Hence, they are used to cure some skin diseases, malignant tumors, etc. Tumor detection and treatment. Dental problems. X-rays are also used in dental imaging to diagnose cavities and other issues. Today, X-rays are essential for detecting cavities, impacted teeth, and other dental issues. Especially designed dental X-rays for identifying tooth cavities or tooth decay. Especially designed dental X-rays are flexible and can be installed in dentist room with direct display on the monitor. Foreign objects. X-rays can help locate swallowed items or other foreign objects in the body. arthritis and osteoporosis. X-rays can help diagnose arthritis and assess bone density changes associated with osteoporosis. Note here in the picture of damaged spine. Arthritis and osteoporosis. Osteoporosis is often called a silent disease because bone loss can occur without noticeable symptoms in the early stages. However, as bone density decreases, individuals may experience back pain, loss of height, a stooped posture, and increased fracture risk from minor falls or even everyday activities. X-rays are used in procedures like arteriograms. An arteriogram, or angiogram, is an X-ray imaging test that uses a special dye to visualize the arteries. It may identify blockages, narrowing, or other abnormalities in the blood vessels. This procedure can also be used to examine arteries in the heart, brain, kidneys, and other parts of the body. CT scans, also known as a computed tomography scan, or formerly called computed axial tomography scan, CAT scan, is a medical imaging technique that uses X-rays to create detailed cross-sectional images of the body. CT scans is a non-invasive procedure and help doctors diagnose a wide range of conditions by visualizing internal organs, bones, soft tissues, and blood vessels. How a typical CAT scan, multi-exposed pictures of X-rays, looks like. Mammography. For breast cancer screening, mammography is an X-ray imaging method used to examine the breast for the early detection of cancer and other breast diseases. It is used as both a diagnostic and screening tool. A radiologist will carefully examine a mammogram to search for high-density regions. Mammography. These areas could represent many different types of abnormalities, including cancerous tumors, non-cancerous masses, called benign tumors, fibroadenomas, or complex cysts. Radiologists look at the size, shape, and contrast of an abnormal region, as well as the appearance of the edges or margins of such an area, all of which can indicate the possibility of malignancy, i.e. cancer. Fluoroscopy. Fluoroscopy is to guide procedures like catheter insertions. In cancer treatment, they are employed in radiation therapy to target and destroy cancer cells. Guiding medical procedures. X-rays can be used to guide the placement of catheters, stents, and other medical devices during procedures. Checking tube and line placement. X-rays can help verify the correct placement of tubes and lines after surgery. Monitoring treatment effectiveness. X-rays can be used to monitor the progress of treatments and identify potential complications. Radiation therapy, often referred to as radiotherapy, is a cancer treatment that uses high-energy rays, including X-rays, to damage and destroy cancer cells. It's a common treatment for cancer, used to cure, control, or relieve symptoms. X-rays are the most common form of radiation used in external beam radiation therapy, where beams are directed at the tumor from outside the body. A typical radiation therapy laboratory. How radiation therapy works. Radiation therapy damages the DNA of cancer cells, preventing them from dividing and growing. The body then eliminates the damaged cells, while radiation can affect healthy cells too. But cancer cells are more vulnerable because they get divided more rapidly and don't repair damage as effectively. X-rays for size measurement of organ determination. Applications of X-rays in industries. Because of high penetrating power, X-rays are used to investigate the structure of metals, crystalline solids, alloys and complex organic molecules. Note here how defects are visible on X-ray film. X-rays are employed in industry to detect defects in tires of plane and motor, golf and tennis balls, and wooden and other item of insulating materials. Non-destructive testing, NDT, of tire. Non-destructive testing methods, such as liquid penetrant testing, PT, X-rays and ultrasonic testing, UT, are used to detect flaws in the tire's structure after manufacturing. PT involves using a fluorescent liquid that penetrates surface flaws, which are then revealed under X-rays or ultraviolet light. Non-destructive testing are also used in testing the uniformity of insulating materials. Industrial radiography uses X-rays for inspection of industrial parts, particularly weld. X-ray non-destructive testing, with its ability To inspect the internal structure of objects finds many applications in the defense and aerospace industries where precision, safety, quality, and reliability are paramount. X-ray may be used to inspect castings, aircraft or machine parts and munitions for internal defects. Quality control. X-ray inspection can also be used in various industrial settings for quality control, ensuring the integrity of materials and products, and preventing defects. In addition, security type applications are common, including the screening of vehicles, cargo, personnel and suspect objects, using either fixed or portable systems. Non-destructive testing is used to inspect welds, pipelines, or aircraft parts for defects. Quality control. In manufacturing, to check for internal flaws in products. Non-destructive testing, material analysis, and precision measurement across multiple sectors. Another widely used applications of X-rays are in security. X-rays are widely used in security applications to detect prohibited items and threats in luggage, cargo, and even people at security checkpoints. They are essential for airport security, border control, and various other security-sensitive environments. This type of scene are common now. Airport security. X-ray machines are commonly used to scan passenger luggage, including carry-on and check baggage, to identify the potential threats like weapons, explosives, and contraband. Dual energy machine to get color images on monitors. Cargo screening. Similarly, X-ray technology is employed to screen cargo, containers and packages at airports, seaports, and border crossings to prevent the smuggling of illegal items and dangerous materials. X-ray car scanning system at border controls. Dual energy X-ray advanced systems use dual energy X-rays, which can differentiate between different types of materials based on their atomic numbers, making it easier to identify organic materials, like explosives, hidden within inorganic materials, like metal. Body scanners, backscatter X-ray, and millimeter wave scanners are used to detect objects concealed under clothing. Detecting trace amounts. X-ray technology can be used to detect trace amounts of explosives or narcotics on surfaces or within objects, helping to identify potential threats. Note: full body scanner. Artificial intelligence software detecting objects on the human body X-ray image. In transmission, penetrating body scanner. Scientific applications of X-rays. Material analysis, X-ray diffraction, XRD, and X-ray fluorescence, XRF, analyze the composition and structure of materials, such as metals, minerals, or chemicals. X-ray diffraction, XRD, is a powerful technique used to study the atomic and molecular structure of crystalline materials. By analyzing the scattering patterns of X-rays, we will review some history, an overview of X-ray diffraction, building on the context of the X-ray tube's development. Max von Laue, a German physicist, in 1912, discovered that X-rays could be diffracted by crystals, demonstrating their wave-like nature and the ordered atomic structure of crystals. He passed X-rays through a copper sulfate crystal, producing a diffraction pattern on a photographic plate. This breakthrough earned him the Nobel Prize in Physics in 1914. William Henry Bragg and his son, William Lawrence Bragg, developed Bragg's law, that is, n lambda equals 2d sine theta, which describes the conditions for constructive interference in X-ray diffraction. This mathematical framework enabled precise determination of crystal structures, earning them the Nobel Prize in Physics in 1915. Their work laid the foundation for X-ray crystallography. Structure determination with X-ray diffraction. From following diagram. Note: X-ray diffraction, XRD, is a technique used to determine the arrangement of atoms in a crystal using Bragg's law, that is, n lambda equals 2d sine theta. The development of automated diffractometers and synchrotron radiation sources revolutionized X-ray diffraction. Synchrotrons allowed analysis of smaller or less ordered samples, while computers enabled rapid data processing. For complex structures, like proteins. X-ray diffraction, XRD, has evolved with high-resolution detectors, microfocus X-ray tubes, and powerful computational tools. Applications now include real-time studies of dynamic processes, nanomaterials, and thin films. Techniques like powder diffraction and single crystal diffraction are standard in fields from geology to pharmaceuticals. Scientific applications of X-rays in physics and chemistry. As wavelength of X-rays is comparable to the interatomic distance in actual crystals, X-rays are used in experiments to study atomic and molecular structures, such as in crystallography to determine protein structures. X-ray, photoelectron spectroscopy. X-ray, photoelectron spectroscopy, XPS, is a surface-sensitive technique used to analyze the elemental composition and chemical state of materials. It works by irradiating a sample with X-rays and measuring the kinetic energy of emitted photoelectrons. This allows researchers to identify the elements present, determine their oxidation states, and understand their chemical bonding. X-ray, photoelectron spectroscopy, works by irradiating focused X-rays from source on a sample, measuring the kinetic energy of emitted photoelectrons. Applications of X-rays in agriculture fields. X-rays may be used in the agricultural industry for quality control and to ensure the safety of produce. Foreign objects or contaminants may be identified and produce sorted according to size or quality. Since X-ray visualizes the internal structure of objects, it is possible to inspect produce, such as olives, to ensure that the pit has been removed. Applications of X-rays in oil and gas fields. X-rays non-destructive testing method for the inspection of pipelines, valves, and pressure vessels. Provide immediate, high-quality imaging. X-rays 3D computed tomography, CT, enables the internal structure of objects to be examined rapidly and non-destructively. CT may be used to inspect castings, to identify defects, such as fractures and porosities. Specialized CT systems may be used to inspect pipelines, providing detailed cross-sectional images for verification of integrity and flow assurance. Applications of X-rays in pharmaceutical industry. X-rays are widely used in the pharmaceutical and medical device industries to ensure product safety and quality. Inspection may be performed on the blister packs, vials, syringes, as well as on medical devices. Examples of X-ray inspection. Use cases are detection of foreign objects, contaminants, identification of missing or broken components, checking fill levels, checking seal integrity, checking for damaged packaging, inspection of simple or complex medical devices, to verify correct content and assembly. Inspection of wind turbine blades. X-ray technology, in particular 3D computed tomography, CT, enables rapid non-destructive, detailed inspection of the internal structure of wind turbine blades to reveal defects. It could otherwise lead to costly catastrophic failures. X-ray inspection reveals material thickness, and structure, as well as uneven bonding, porosity, discontinuities, and undulation. Ultra-high resolution X-ray imaging of 3D objects. Illustration of a flexible X-ray detector that is suitable for imaging 3D objects. It consists of a sheet of a transparent polymer embedded with luminescent nanoparticles. Archaeology and art. Examining artifacts, paintings, or mummies to reveal hidden structures or compositions without damage. Authenticating artworks by analyzing underlying layers. X-ray art. X-ray art artists. Use of X-rays for their imagination and artwork. For example, the works by Stain Jagodic. X-ray astronomy. X-ray telescopes detect high-energy phenomena like black holes, neutron stars, or supernovae. Chandra X-ray space telescope. Chandra X-ray space telescope picture. Picture of supernovae by Chandra X-ray space telescope. The Sun in X-rays, as seen by the NUSTAR observatory. Active regions are the brightest in X-rays. Comparing picture of Jupiter of X-ray telescope and optical high-resolution telescope. Thank you very much for watching this video. Please continue to watch our other videos. Subscribe this channel. Thank once again.